So far, you know how to find the least square regression line for a given data set. This is an example I used before, that the resale values of used cars using the mileage, that data set. Okay, we used this example before. So in this example, the way we figure out the least square regression line, first by finding the R value for that data set, for this data set, the y here and the x here. So we calculate this and add them up and then divide by n-1 to figure out R. Then we use R value to figure out this estimated slope as well as the estimated intercept. Okay, so in other words, once we for the data set you figure out the R. So once you figure this thing out, so the slope is going to be R times whatever this value times Sy divided by Sx. So you need to figure out those two values for this data set and this data set, this data and this data. So you use that to figure out the slope and the intercept using this formula. And that will give you the estimated the least square regression line, the y hat. So this value estimated intercept 32.962 minus the estimated slope, this times x. So this is the least square regression line. So at the time I told you that I will give you another way to figure out that. So either you can do it like that or you can use this formula. Okay, so the formula, the slope, you can calculate using this formula. It's going to be the sum x times y. So in other words, this value times that, this value times that. You need to take the product and add them up. Okay, so in other words, this times that is 30. So I'm writing the product here. This times that is 50. This times that is 40. Like that. When you add them up, so that is 230. So this value is 230. Okay. So times n, the number of the pairs you have. So here you have pretty much the 5 data points. When I refer to a data points, I'm referring to the one pair. Okay. So 5 data, n equal 5. So so that times x bar, the average for that. Okay. So that times the average for that y bar divided by this quantity, which is, this is the going to be, if you remember that the sample variance for the x values, that is going to be n-1 times the sample variance. So the way we define the sample variance, basically this quantity in the denominator divided by n-1. Okay, so anyway, the bottom line is that this the denominator is going to be n-1 times the sample variance. Okay, so that will give you, you can calculate, use this formula if you want to, or otherwise you use that formula. So either way you will get the same mass. Okay, so once you figure out the b, then after that a value is the same way. A value is y bar minus b times x bar, the same way we did it over there. Okay, so we can do that. So anyway, so you can do that way. So now the thing is that once we get, now we are going to go into the how to figure out, say for example, confidence interval for the slope, or the confidence interval for the intercept, where this is going to cross that, or the other way the slope. Okay, or the other way you might wanted to see whether this slope is 0 or less than some value, something like that. The testing, in other words, we are heading towards the testing and estimation. Okay, so confidence intervals. So that's the basically what we are trying to get into next. So for us to do that, we need to have some model assumptions. So the model assumptions is this way. So I'm in general. Okay, so this is a data, suppose have a positive trend. Okay, so for the x and the y, whatever that. So for given x level, you can, the assumption is that the y is going to have a normal distribution with mean. So I am going to change that, instead of using simple a and simple b, alpha for a and beta for b. Okay, so that's a very standard notation. So in statistics we use alpha and beta, the Greek letters, for the parameters. So I'm going to switch into that. Okay, so in the before we use the a and b here. Okay, so anyway, so what is going on here is that basically what we are doing is that, so for given x level we are assuming the distribution of x has a distribution of y has a normal distribution. In different words, so what we are saying is this: for say 2-year-old car will have a different prices. If you can collect all the data for 2-year-old cars, that is going to follow a normal distribution. Okay, so that's the assumption. For 3-year-old cars, again with a different normal distribution, like that. The 4-year-old cars are the same way. But when you collect the data, we don't get so many data from each level. Okay, but the thing is, the assumption is that if you can collect a lot of data from that, once you fix that x level, the data coming from the same level will have lot of if you collect lot of data, will have a normal distribution, like that. Okay, so the assumption is that for each level this is going to follow normal. If you connect the mean levels, the mu values, mean value for y for given x, that is going to follow a linear trend. Okay, in other words, if the data is going to follow a linear trend, that's where we are going to use this method. Okay, so the linear model. Linear means that there's no quadratic term, or that linear in terms of parameters, a straight line. Okay, so anyway, so that's the assumption. So the variances for this each normal, that is going to have a same variances. So basically for these assumptions, we have 3 parameters now. One is that for this linear, the mean trend, so the slope is the beta for that line, the intercept is going to cross that y-axis is alpha, okay, and the variances of this each curve is going to be sigma square. So what we are going to do is that we are going to estimate these alpha, beta and sigma square using our data. Okay, so in different words, this is a simple way to write that. For each level of x, the y is going to follow a normal distribution. So this is the theorem actually. So I'm going to kind of do it in a very summarized way, okay, because I really don't have time to do this one now. So in the summarized way, I'm going to do it. So under these assumptions, one can show that the beta hat is that the estimated least square estimate for the what you have seen before is the b, least square estimate of b, which is the least square estimate of beta. So either that or the other way around. I gave you the 2 methods I gave you. You can use either method, okay? Whatever the answer coming out of that, either this method or this method, doesn't matter, okay? So if you use this, it's the same answers anyway. So that, I was writing the second method here. So that is the one I am writing, the estimated value. You remember that when we talk about a parameter, we use the hat for the estimated value. I am doing the same thing now, beta hat. For the alpha estimated thing, I am putting a hat, okay? So the least square regression line with this thing is going to be the y hat equal alpha hat plus beta hat x. So this beta hat will follow a normal distribution under these conditions with a beta, with that unknown beta, the unknown beta value I'm talking about here, and the variance for that is going to be the sigma square divided by SXS. So this value is defined like this: sigma x minus x bar s square. So this is, in different words, you have seen this part before actually. You have seen it when we figure out this piece. So this piece was this part divided by n minus 1. Alright, so therefore of course this part is going to be n minus 1 times that s square. So this is the sample variance for the x values. The same way, okay, so let me finish this one. So in other words, so that is that, okay. So of course if you standardize this minus beta divided by square root of that is going to follow the z curve under these conditions. You remember that then we went from the normal to the other one. Once we use the estimated value, they got into the t distribution. The same thing happens over here as well. So once we replace that sigma by the estimate, I will tell you the estimate in a second. So I am using that estimate with a hat now. So once I replace this thing by the estimate, okay, so I have everything the same except that I am replacing this thing by the estimate. This will follow a t distribution with degrees of freedom n minus 2. Okay, so that's coming from a theorem. So so this sigma hat this is how you get it. So the sigma hat, so there are two ways you can get it actually. One way to get it is that using this simple formula. Sigma hat square, use this formula. So this formula is yy is defined by this way. Okay, so in other words, again, this part is similar to that. So you can figure out the sample variance for y and times n minus 1, the same way we did it over there. Okay, that's one way to figure out that. So anyway, the bottom line is this part is that, or the and syy, this one is going to be this product. But let me show you the way it's handled in your the book, okay. But the point is that this is a very common notation, okay, that there are shortcut formulas for that. That's why I'm giving you this, okay, because most of the time later on you're going to see this if you go far enough in here, okay. But anyway, so this is how the book is dealing with this piece. So the residuals means that, so once you get this fitted line, the least square regression line, you have the line, which is this baseline. Once you have this baseline, so for each data point, you have the each data point minus the fitted value. Okay, so in other words, the difference between the value minus the fitted value is known as a residual. Okay, so the actual value minus the fitted value coming out of this formula. So once you get this, so you need to basically calculate for each data point this value. So once you calculate that, okay, so for each actual data point minus the fitted value, take the square, add them up, divided by n minus 1. Okay, so that is that estimate actually. So in other words, this is the error. Basically the actual value minus the fitted value, and that when you add them up, square them and add them up, divide by n minus 2, and in your book is denoted by simple s square. So I'm going to use this same hat thing, okay, so because it's the estimate for that. So this is the estimate, or if you want, you can use the simple s square. So if you use the simple s square or that sigma, this is the same thing. So in here, this will follow the t distribution. So anyway, so this is what we use to do the testing, to check whether the beta is equal to 0 or more than 0, or to construct the confidence interval for beta. So we are using this curve, okay. So I will show you this one in the next video, okay, because 15 minutes it's up almost, okay. So in the next video I'll show you that.